Linear probabilistic modeling is a method to represent a set of binary outcomes as a simplified equation using linear regression on the data. The equation given by the linear regression represents the average probability, which is the y-axis, of a binary outcome which accumulates relative to the x-axis. We see linear equations frequently throughout life, for example, a mileage rate in a taxi, or the amount you're paid for hours of work. As your hours increase, which are the x-axis, your pay should increase as the y-axis. A large majority of things within our day-to-day life can be represented by graphs like this. This makes it generally easy to understand logically and is a reason why linear probabilistic modeling is effective within statistics. So linear probabilistic modeling is unique because the y-axis varies between 1 and 0, while the x-axis can be any sort of variable such as time, speed, temperature, etc. In the example shown, we have a set of data which can be gathered from any source, but in my case, I made up. It shows the results of car crashes at different speeds, with the x-axis being miles per hour at impact, and the y-axis being the binary result of the passengers dying or living. While this is obviously grim, it is the sort of life or death situations that we often have to deal with in engineering due to the large risk factors involved. Through linear regression, an equation is created that should be somewhat familiar as it is a normal linear equation. This is y equals b0 plus b1 times x. So the engineering example is the car accident deaths, and the graph is a linear probabilistic model. As it can be seen, the y-axis represents the probability of death during a car crash as the speed of the car at the moment of the crash increases. The line is a linear regression equation and is used to represent the average probability of death per mile per hour. From this relatively small amount of data, we're able to create an equation that can be used to find the average probability of death at any speed. This is useful because often in engineering, we have values that have never been seen before, and we need to be able to make an educated risk assessment based on the data that has already been gathered. In the case of this example, if we wanted to know the risk of death for an accident at exactly 50 miles per hour, because that is the speed limit of the road being developed, we would simply plug in 50 to the equation and get a y value equal to the probability. It's very important to note that the equation will become more and more accurate as more data is gathered, and that this is only an average probability. There are many factors that could determine individual risk of death during an accident. This approximation is most useful for risk analysis and can give an engineer a relative understanding of the relation between the speed of the car and the danger it poses.